All right, I'll give everyone 2 minutes before we start.
Okay.
Just welcome everybody though. It's going to be a very interesting session. This is really for when everyone thinks that FTP is all they ever need for file transfers. Ben will dissuade you from that to understand that no, that's not going to do the job. There are cases when you need real fast transfer technology. I can think of things like I'm in Houston, Texas. You know, we've got things like oil wells being monitored remotely by video. We've got IoT devices spouting out data from all over the place. We've got retail stores sending huge amounts of data back and forth. FTP is not going to cut it for all those use cases. So that's why Aspera exists. It's to handle that and more. That's just my personal use cases I thought of. But so this is going to be an hour long. If you have questions, please put them in the chat here at the moment. And if we don't get to them, there'll be an office hours after this where speakers will be on there to be able to answer questions live. There's a tech community. We'll be posting that link in a minute. So for blogs and for information, for everything else, it'll be on there. At the bottom of this page that everyone's looking at are the actual slides, just in case you get called away and you need it. And these videos will be recorded and be available later on YouTube and also on this page. So with that, I just want to start. So Ben Forsyth, he's Chief Architect for IBM Aspera, and he'll be going through why Aspera is really what you need for fast transfer technology. So Ben, over to you.
All right, thanks so much, Frank. Thanks for the wonderful intro. And yeah, FTP doesn't always cut it, and I'll for sure get into some of those details. So yeah, as Frank said, I'm the Chief Architect for IBM Aspera. So in this session, I'll give an overview of TCP-based network protocols and highlight some of their deficiencies, and then talk about the Aspera fast technology and how it addresses those deficiencies. Then once we get through that, I'll transition into some of the use cases where customers have built out transfer technology and workflows with the Aspera transfer at the heart of those use cases. So there we go. All right, so first we'll start off with just a kind of simple network primer about TCP and UDP. We'll transition into why problems exist with TCP, then get into the use cases and with web applications, and then a tad bit on observability and transfer reporting. Okay, so first we'll start with the network protocols. So these are, say, the most common network protocols that are out there. Pretty much every network protocol that you would use in day-to-day work is built on these two things. So sort of the foundation of all of them is something called IP. So that's everybody, I think, is pretty familiar with IP addresses or DNS names. Each one of those IP addresses in the IP protocol also has another portion of it called a port, and IP uses the combination of source IP, source port, destination IP, destination port to route traffic. So it's how routers are sending packets around, and network address translation is finding which hosts are sending which data. Let's see. Next, UDP. So UDP is sort of below IP. So IP is the top stack. Then below that is UDP. There's a small header that constitutes what an UDP packet is. The most common use cases I think you come across with UDP are for DNS lookups, and most likely what's happening behind the scenes here on in this streaming session is things like VoIP are going to be using UDP packets to sort of translate our or one's voice into waveforms, and then sort of blast that over, get compressed, and then on the other side, it's gonna kind of uncompress that and make your voice be heard on the other side. One thing about UDP is it may never make it to its destination. So for data transfer, that becomes somewhat problematic. So a sender sends the UDP packet, and a receiver is not guaranteed that it's ever going to get it. So to handle all of that, TCP is sort of built on top of that. It's the most common network protocol for user applications. It's the foundation for, say, HTTP, at least version 1, version 2 of that, for FTP, other very common file transfer protocols. And what TCP does is it makes guarantees that every packet will be received. And the protocol itself handles that. So as a, say, application developer, if I'm sending data with TCP, I can just write a buffer of data or read a buffer of data, and it's kind of guaranteed that that write will get to the other side, and when somebody reads it, it will be exactly the same amount of data that was sent. In order to do that, the TCP must acknowledge every packet that it sends and receives. And it uses some very specific algorithms to do that, and those get sort of changed over time, and there's slightly different implementations depending on your operating system, depending on the sort of vintage of your computer. But the maybe most important thing is that it just works, no matter what kind of vintage of computer you might have or a mobile device. It's all back compatible, and so an old TCP client will work with a brand new one, and everything will just work. So that back compatibility and capability of having data always consistent and always being received comes at a cost. And that cost I'll kind of highlight here. So with TCP, what we have to do is, because we're acknowledging every packet that we send, it needs to buffer data. And the longer the distance, so that's what we're showing here, the round trip time, the more data it needs to hold to acknowledge back to the other side. And that buffer is kind of, it's finite. And that introduces, it's called the sliding window problem. And that introduces this graph here. And what that's showing is the sort of large bar in the top left means when there's no latency and no packet loss, TCP can go at sort of full line rate. There's really no problems in sending data, and there's no problems with speed. And that's because the amount of data that needs to be buffered is so small because the acknowledgements are so fast. However, as you introduce latency and packet loss, TCP can't buffer that much data, and so the way it deals with it is it slows down. So it drops throughput. One more point to note why packet loss affects it is the way it deals with packet loss in different rate controllers and TCP maybe deal with it slightly different, but in general, it drops the speed by half, and it does so increasingly until all packets can be acknowledged, and then it will speed back up, and then you'll have loss again, and it'll slow back down, and you get what we refer to as a sort of sawtooth pattern. So what this results in is any applications that are relying on TCP, like FTP, that have any packet loss or any latency, so essentially using the internet, are going to be relatively slow, and they're going to be capped at certain rates just due to network latency. And that latency comes into play it's really the sort of copper or fiber that exists between two endpoints. So, speed of light is very fast, but as that speed of light, if you will, goes through routers, goes through networks, goes through different public sectors over the internet, there's limitations on how fast that will be. So, how the IBM Aspera solution deals with that is something unique. And you can see this graph is quite different from the other one. And essentially, loss and latency really don't have the same effect that they do on the TCP-based transfers. So it's called, we call it FASP. So it's the FASP Adaptive Secure Protocol. So it's based on UDP, and it uses a control systems approach to measure the network bandwidth and then automatically adjust the rate of transmission based on those measurements. So the common use case that I think most people can relate to, especially if they have newer cars, is cruise control. So maybe in older cars, cruise control only kept you at a certain speed. So I'm out on the highway, on the freeway, I set it at 55 and it will just kind of go at 55. If I start going up a hill, it will sense, hey, you're going a little bit slower. Let me go faster up to 55. Newer cars, they'll even slow down. So if I'm in traffic, the cruise control will react to the traffic and it will slow me down to 45, 35, whatever the sort of freeway or highway speeds are going at, the cruise control adapts. So the Aspera FASP solution really works in the same way. Rather than using speed, we're using the round trip time. We're also taking packet loss into account. And what we're attempting to do is find the steady state, the maximum rate at which we can go with being as efficient as possible without losing any speed and without losing any packets. So we're constantly measuring these things, feeding them back into our algorithms and coming up with the optimal speed that's going to be most efficient as possible. So since we're using UDP to overcome that, we do have to deal with lost packets, because packet loss will happen over the network. And so we built in the protocol a mechanism to understand ranges of packets that have been sent and acknowledging the highest packet number that we've seen. And that's how we can prioritize retransmission of packets and how we can minimize the packet loss, since we're keeping track of all of those. In addition, it's secure because we are encrypting every packet. So each time a transfer starts up, we generate an ephemeral key. That key is used to encrypt every packet. And that's how we manage security. Let's see, what else can we say about it? Oh yeah, we did selective acknowledgement, right? And we're constantly sending the round trip time and loss between the sender and the receiver, and we're using rate algorithms to figure out the optimal speed and send it back. So next I'll go just about. Yeah, to sort of show practical examples of moving a 10 gigabyte file. And what you'll notice on the bottom, the numbers, they don't really change. So what we're really saying is the distance that's involved, sending data from across the United States, between the US and Europe, between the US and Asia, all of those are going to have different round trip times, and they'll affect TCP and different loss characteristics as well. They're going to affect TCP in certain negative ways. And what we're sort of highlighting in this slide is that that variability ends up, in the say US to Asia case, making transfer really impractical. That with the Aspera fast technology, it's always going to be sort of exactly the same, in that we'll fill the pipes as much as we can, and we'll get the same times for those data transfers. So the general math that I kind of remember is that 1 gigabit is 125 megabytes per second, and so that's where you're seeing those numbers as it's taking that math and giving you the times based on that. One point to note with the fast technology is storage. So I think I mentioned in the prior slide that we're measuring round trip time, and we're trying to find a steady state. Well, one of those variables is reading from storage and writing from storage. So we'll only go as fast as our slowest leg, if you will. And when that slow leg happens to be storage, that's one of the factors that we take into account in our rate module calculations. So if we are, say, the network can sustain a gigabit or more, but storage can only sustain maybe 100 megabits, we'll adapt our rate automatically to go at 100 megabits because we'll see that storage is slow, and yeah, we can only go as fast as the slowest link. So a key point there is make sure that your storage is tuned, as well as nearby where your transfer servers happen to be. Okay. Let me talk a little bit more about transfer efficiency and something we call good put. So mentioning rate control and steady state and these things, what we really want to do is eliminate data loss, and we want to go as fast as possible without inducing loss. So essentially what happens when a router gets too busy is there's a kind of a queue of packets that it needs to send. And so as routers get busy, those round trip times will increase. So that's how we sort of sense congestion. Routers will have policies as well. If a packet is in a queue for too long, it may just drop that packet and say, well, it's stale, what have you, we're not going to forward it. Or maybe buffers in the routers were filled, and that packet could have never been received or acknowledged. So loss, let's say, is really inherent in transferring data over the internet. And what the Aspera transfer is doing is measuring that loss, measuring those round trip times, and trying to find the optimal speed at which to send it. So what I highlight in this slide is that if you lose a packet, you have to resend that data, and you're going to end up sending more data. So in this example, we're saying, okay, we need to send a terabyte of data. And if we have a gigabit available, we know that using the math I referenced before, we can send about 125 megabytes per second. 1 terabyte is 1,000 megabytes. If I divide that by 125, I have about 8,000 seconds. And that's kind of the math that I would do to figure out, okay, my network can transfer at best this amount of data. So what I kind of have in my notes here, we can do a terabyte at a gigabit. I can do 10.8 terabytes in a day. So you can do the math and figure that out. And in this case, we can do 1 terabyte in about 2 hours and 13 minutes. Again, just based on the math. However, if there's packet loss, I'm going to have to resend data, and that's going to change my rates. So, for instance, if I'm losing 1 out of 10 packets, and that's a fixed amount, because if for every 10 packets I send, if I lose 1, then my loss can get crazy and almost exponential loss. But let's just say that out of every 10 packets, one gets lost, and when I resend the next set of packets, it doesn't get lost. So if we just say we're losing that amount, we'd go back and say, okay, well, if we're losing that amount of data, we're going to have to send not just 1 terabyte, we're going to have to send 1.1 terabytes of data. So we're going to have to send more data. That's going to take more time. And again, just doing the math of what the sort of data rate per second ends up being is it plummets our data rate. So even though our network could say sustain a gigabit, my true transfer rate, or good put as we refer to it, will come down. So in this example, we're saying that the good put is actually 880 megabits, because we're going at that 125 megabit per second rate, but we had to send 1.1 terabytes. So we're bringing the network rate, we're bringing our true rate of transfer down. And what we really want to do is maximize our transfer rates, but keep it at that steady state where we're not losing packets, we're not dropping packets, we're going at what the network can allow, and that's all automatically. So no tuning required. The program will take care of it, and that's really the value add for the Aspera fast transfer, is that we automatically adjust our rates, we sense when there's congestion, and we optimize that to go as fast as possible. So I'm going to transition to another slide here, and we're going to talk about the products that use these technologies. So let's say the flagship product, something we call the high-speed transfer server. It provides file transfer, synchronization, automation, and APIs to be able to report on transfer, access storage, and initiate transfers. So we have a suite of web applications that use the APIs, for example, to render views up in a web application, and also to initiate transfer. Then we have a product specifically tailored towards streaming, and it's meant to plug into a TCP-based workflow, and it acts like a proxy server, almost like a VPN tunnel, if you will. And it's used to sort of stream data from one location to another. So a couple of use cases that we have for Fast BIO is database replications, where you need to stream data from a database in one location to another, as well as doing like data migration of like HDFS Hadoop file systems, or Artifactory repositories, where you need to do this kind of mass migration. There's existing TCP-based tools that are very specific to that implementation of an application, and we can plug the FastBio gateway in the middle of those. Okay, so here is kind of the architecture diagram of the high-speed transfer server. The primary application is called ASCP, so it's a command line tool. And if anyone's ever used the Unix tool Secure Copy, SCP, then you'll be familiar with how ASCP works. So it uses SSH initially. We can use HTTP as well. Uses SSH to create a TCP-based control channel. and then it starts ASCP in the server mode on the server side. All sides exchange, say, command line options and server configuration options, as well as the ephemeral key that I mentioned a couple slides back. Once they do that, they start sending their UDP data, and then the Aspera FASP protocol takes over. The TCP channel is used as the kind of file transfer protocol, if you will. So we're using TCP to make requests and get responses for every file that needs to be transferred. So you give ASCP an argument, say, to a directory. Maybe that directory is a giant tree that contains hundreds of thousands or millions of files. And we're going to be using the TCP channel to make requests for every file, make sure it's on the other side or not on the other side, and we'll determine if we need to transfer the file. So there's options in ASCP to sort of skip files if they already exist, check checksums on them, make sure they're the same, and so we won't end up transferring if a source file and destination file are matching. For synchronization, our program is called Async. So if you're familiar with the Unix tool called rsync, Async was sort of built with that in mind. What it can do is it optimizes synchronization by keeping a local database of the last state of the files. And when you run a new async session, it compares that database with the current state of the file system. And if there's any changes, then it will attempt to synchronize that file to the other side. But if there's no changes between the current state of the file system and the last time async ran, then it won't even attempt to synchronize that file. There's different modes that it can operate in that can sort of force that to happen, but to make it as efficient as possible, we really compare those two states and attempt to synchronize only if the state is changed. So then Aspera Node D, that's our API server. We typically front it with Nginx. That's what's saying there. It can be used to initiate transfers through an API payload. It can also browse file systems and interact with file systems. So deleting things, listing things, moving things. And as I mentioned, it's used heavily by our web applications. For automation, we have a component called a watch folder. So it's configured through APIs, and what it will do is it watches a directory for changes, and when files are added, it will trigger a transfer. So it uses file system notifications to do this, but it also has periodic scanning to look for changes, and it uses something similar to async to compare the current state to sort of the last known state, and will only trigger a transfer if the state has changed. Some interesting use cases for watch is get into the use cases a little bit now. Is we work with a broadcaster that does a lot of live sports events. So they use the watch folders to take the data that's coming from the cameras into the trucks, onto storage on the trucks. And when the sort of processes that they're using to I don't know, synchronize the video maybe or finalize video is done, the watch folder will trigger transfers up to cloud-based transfer servers for archival purposes, as well as to editors that may be in remote locations, so they can edit the files, reformat them for different content viewing. So maybe for web, for mobile, for halftime shows, and this type of thing. So it's a pretty interesting use case for the watch folder. Okay, so let's go to our next one. So yeah, we'll talk a little bit about some use cases and Yeah, this one is with our packages application. So the way that you can think of packages working is it's like an email style attachment workflow. And what you'll want to do, you'll have a use case where, say, you want to deliver a file or a number of files, and that needs to be kind of an atomic unit. So with synchronization, I might be synchronizing maybe hundreds of files, but the other side won't necessarily know when I'm done. So if you can imagine, two endpoints are synchronizing to a central place in the middle. If I start at, say, T0, I start uploading files, and then I'm going to start my synchronization at, say, T1. I might get a couple of files based on the synchronization that started at T0, but I might be all complete before T0 has completed. So with the package mechanism, what we're saying is we take a transfer. It has one or many files, and when all of those files are transferred to that middle point, then we'll trigger a notification that lets the other side know that, hey, we're complete, and I can download this package in its entirety, and everything will be there. So it's really a kind of atomic way, kind of just like you get a package in the mail or delivered. It contains everything. So it might have been that had to be obviously assembled, and not everything went into the package at exactly the same time. But what arrives at your doorstep or your garage is the full package with all the parts and pieces in it. And so that's really our packages workflow. And it's very common to use it in media and entertainment, but other industries where you need to have these atomic units be transferred from one side to the other. So the way it's used is, you create a new package, you add recipients, and recipients can be individuals, they can be groups. We have a feature called a shared inbox, which is a kind of a group-like concept. You'll send the package with our client application. It's through a web UI. The recipient will get a notification through email when the upload is complete, and then they'll be able to download the parts of the package. It's also great for automation, because we'll have API clients that will subscribe to those package events, and when they get a package for them, they'll be able to trigger transfer. And so you can build very robust workflows with the package automation technology. So we're just highlighting here that post-production, title, sound, VFX, what have you. So email and APIs run on that, and then thousands of customers per week in disparate places. So email workflow. Okay, so let me go on to the next use case. Sorry, getting a little ahead of myself. So this is how our packages user interface works. So this is highlighting that these are the packages that I've received. If I can see my transfer activity, those are all the sort of packages in flight. And you'll see in the UI, I have a little button to send files. When I click that, that'll pop up a little dialog, and I'll type my mail message. I'll give it a title. I'll add my recipients, and then I'll attach my files, and I'll click send, and that will trigger the transfers. So we have it in both the SaaS version of this and self-operated. So we operate just a bit on the SaaS. We operate transfer servers that are in, I want to say it's about 27 different cloud regions. So in IBM Cloud, Amazon, Azure, and Google Cloud. And if you have storage bucket. So let's use Amazon Cloud, for example, has Amazon S3. That's a very common use case in for the Aspera transfer. If you have files that need to reside or you're making use of Amazon S3, we'll have transfer servers in those regions, and then you'll be able to use the say the SaaS version of packages, or you could use the self-operated, so you can have a version if you want to run a web server on premises or in the cloud, but your team is responsible for it. That's also possible, and you can build out your own packages workflow. And we have customers that do both. They use their own packages installation. We have customers that skin their own user interface around the packages APIs, and then we'll have customers that use the SaaS version of packages and run their workflows in that way. Okay, I think the next one we're going to get into is with manufacturing, and in this we call it the files workflow. So this workflow really represents like a mounted file system, or what you'd see in your desktop or laptop machine as you navigate through your directories and file systems. So we simulate that in a web UI for manufacturing use case. We have what we call them sort of file shares, if you will. So most people probably used to that. You have different shares that have or different mounted storage that have different sets of files on them, and it's typically it's kind of shared knowledge, or there's maybe documented knowledge of what's in every directory structure, and there's maybe a logical name to the directory structure, so that one knows sort of intuitively how to navigate through that. We have searching capabilities, so those are through the APIs. If you happen to remember where a file what a file was named, but you can't quite remember where it exists in the directory structure, well, you can search in the web UI to find things by names. And then you can click to upload or download either files or folders. The web UI, I didn't really mention it in packages, but we use role-based authentication to allow users to log in. We integrate with SAML providers and integrate with SAML groups, so that based on, say, a SAML membership, someone will be automatically added when they log in to specific groups and have access to specific files that matches their group. So yeah, and very much in this web UI, we make it just like it is on disks. So here I kind of will show what the web UI looks like. So you can see those are some files. We have icons associated with them. If they're video files, we do have the capability to do video playback. So that's showing some of those there. And then I can navigate into those directories, or I can select them to delete them or move them. There's a panel that will come up that will let me sort of drag and drop files between folders so that I can copy them or move them. It could be that some of these, you see that folder at the top, it says automation folder. It could be that folder is on a completely different transfer server somewhere else in the world. So if I need to move files between different storages, I can drag and drop between them, and that will trigger the transfers. So yeah, and this familiar directory navigation, yeah, upload, download, move, delete, rename. So very much like what individuals would be used to when they're navigating through their own file system. Okay, let me go on to the next use case, which is transfer reporting. So all of these transfer activities that that I was talking about before, you also need to know like who did what, when, and where. And so we have a whole reporting engine that's based on the APIs. It's also in the SaaS, so it operates at scale, or in self-operated, which doesn't quite have the same scale that we have to handle in the SaaS. But you're able to kind of have a dashboard view of things that are happening at any one time. We draw these graphs. You can see how fast things are moving, through which users are initiating those transfers. And then we can go back in time and search through history to be able to see who did what, when, and where, to give that transfer reporting and sort of MFA capabilities, or MFT, I'm sorry, managed file transfer capabilities, so that you know, for auditing purposes, you can track who has done what, and where. So this is typically done through APIs. So the web applications will query APIs on the transfer server. In our SaaS, it's a slightly different architecture. It's an event-based system, and that's to give us the capabilities to keep up with all the sort of millions of files and millions of events that are happening through the SaaS. That's a little bit on transfer reporting. And let's see. So now I'm going to sort of finish up with the FastBio Gateway, which is our other product that's done for streaming. And really, what we want to show here is how we can plug FastBio into a TCP-based workflow, and we're able to, you know, the client and server application are sort of never the wiser, let's say, that the data transfer is happening through the Aspera Fast protocol. It will stream the data really just like it would for a VPN. So then the same way you'd connect to a VPN, underneath things just sort of happen, and you can access a site that you wouldn't otherwise be able to access. And so we really try to keep FastBio working in that same way. We're able to stream the bytes without the client and server or sort of end user really knowing that this is happening. So really, I'd say the most common use cases that we do have an integration with IBM MQ Advanced. Database replication is a common use case, and then the Hadoop file system replication. So using a tool called distcp, which is sort of meant to transfer Hadoop file systems. We can sort of plug into that and make sure that those bulk transfers are getting the benefits of the Aspera Fast. So maybe the key thing to point out is that if the TCP protocol is very request response centric, and those request responses are very frequent, you're not going to get a lot of benefit from FastBio. What we really need is maybe a small request and response at the beginning, followed by a bulk transfer, and that bulk transfer of reading or writing shouldn't be interrupted or slowed down by requests and responses that need to happen in the middle. It can be that, you know, you have request responses in the middle, but as long as they're infrequent, then you'll be able to get the benefits from FastBio. But say if you send 5 packets and then you need to get a response every 5 packets, then that's probably not a good use case for FastBio. Okay, and I think with that, yeah, so we just go on the use case for FastBio. So we'll point out distcp So moving petabytes of data from Hadoop, and yeah, so they were able to get those 10 plus terabytes a day, because they had, I think they're able to get well over 5 gigabits a second for this data transfer, and they were able to get the HDFS systems migrated from one location to another in a reasonable amount of time. Okay, and I think with that's covers my presentation. So maybe not the full hour that we had quite scheduled, but it gives us a little time for Q&A if anything came in. So I'll look to Frank to give me a hand there if we got anything, and can go from there.
Yeah, nothing at the moment on questions, but I have a question about for a use case like remote IoT devices.
Yep.
Is that one that you're seeing? Because usually they're in remote places, unreliable connectivity, but they want to kind of stream the data if they can.
Yeah.
In as near real time as they can get. Hard to do because of reliability. But is that something that you're seeing for Aspera as a use case?
Yeah, we've come across them. I don't think we've gotten too many implemented over the years, but that's the perfect use case for a fast IO. So where you have like the one that comes to mind was with cameras. So there were cameras in like very remote locations, and they need that data streamed into a central location where it can be monitored, analyzed, run through AI models, whatever needed to sort of happen. And so if that was a TCP based protocol, there may be a lot of lag in that. What comes to mind, I didn't highlight it, was we have a use case with video streaming, and it's with gambling sites. So they're right. So they're there's a live event, and so I'm at say a location that's streaming that event live, and if I want to make bets on what's happening in real time, that video feed needs to be as real time as possible. Say if it's 2-3 minutes delayed, I could call somebody and be like that at the event, like, hey, what's happening here? I'm in the betting center, and it's how many points are they going to score, or things like this. So we do have a use case for that type of near real time data, and they sort of solved it with the Aspera solution, and sort of worked around it to have it as almost real time as possible.
Yeah, I have a background in technology that was based on UDP.
Okay.
It sits under the floors for the stock markets.
Okay.
For stock tickers, but the problem was we didn't use it for anything really streaming. That it was really just individual messages. We couldn't get it to where it was for actual what you're looking at, which is more packaging it into streams of videos and everything else. So it was good for tiny stuff, but it couldn't handle anything where it was getting into taking large things, breaking them down. So you've got all these streams of data flowing and then reassembling. You didn't mention it, but I'm curious about the Aspera mobile app.
Okay.
As a practical tool, because when you think about it, you're going to have people out in different places.
Yeah.
And mobile is what they're going to have, and they may want a video stream. It could be a worker on site in a place. It could be, because it's ad hoc.
Yep.
Is that something that you're seeing much use of, or are people aware of it yet? That, for example, issue all my workers, maintenance workers, with this app on their phone. They go out and they take a picture or take a video of a power line, of a pole, of vegetation problems, anything like that, so that they're not formally, take a photo, wait a week, do that sort of thing. Is
it's interesting you bring it up because we have kind of exactly that use case. So we have a customer in Europe who developed their own mobile application. We had a mobile SDK.
Yeah.
And there are technicians that are out in the field doing just that, checking its closets and not dishes, but mobile device relay points, access points, antennas, closets, all this kind of thing. And they developed a mobile app to sort of download schematics for the different closets and towers and whatever they may have. So as a tech is going to different sites to work on it, they have the sort of up-to-date schematics of what that closet, what that antenna may need, require, all the kind of details in there. And then they can take pictures of it, send back like lightning strike, this tower was knocked over or whatever may happen, and so they can get the right parts ordered and work to get the thing back online. So we definitely have a use case that's exactly that, and they're using so they use our SaaS infrastructure for the transfer servers, and then they use the mobile apps to be able to upload and download all of that data.
Yeah, I think that's what people, if we've got a couple of people online, this isn't file transfer. That's not the only thing. It's really the idea that I can do things at near real time, as near as it gets, reliably, no matter what the format is that we're talking about, and things like with remote connectivity. You're not going to rely on your sending a message by the usual ways. You're going to be sitting there staring at your phone going, it's not working. And if it's emergency based where it needs to be done in real time, then you need something like this. And everyone is going around with a phone. Everyone is using it as their mobile work device more than a desktop or a laptop. It's great, but it has limitations. So, for example, I'm using good Lord, I don't know how many cloud providers where I'm trying to do simple things like upload a photo onto that cloud provider, and I could sit there and it's basically spinning. It's not working because they don't have anything behind the scenes that's actually doing what Aspera is doing. They're using very basic, and it just try it, times out, try it, times out. Simple stuff like that people don't think about, and that is where things like Aspera, I think, will be very useful going forward.
Yeah, one of the key benefits that I like to highlight is even if you don't have a lot of bandwidth and you can't go that fast, it's going to be reliable. And with the Aspera transfer, it's always going to be the same time. Or say you have 1 megabit of bandwidth or something on a mobile device. With TCP, you might be able to transfer a 10 meg file in 5 minutes or 30 minutes or an hour, and you'll have all this variability. But with the Aspera-based transfer, it'll be the same every time. There's really, you can kind of bank on those transfer rates, because sure, we might slow down if we sense congestion, but we'll speed back up when the congestion passes. But however it will be reliable. So in pretty much the same time, you won't have a bunch of statistical difference over time as you're transferring data. And with TCP, the variation can be wild. It can be all over the place.
Yeah, and everyone's dealt with the 90% downloaded, failed, start again.
Yeah.
So that reliable as number one is the big part. I'm curious, and I may have missed it. What about compression? Is compression part of it? If I want to, I've got limited bandwidth. So think of something like an oil rig sitting out in the Gulf of Mexico, Gulf of America, wherever you want to call it. The bit of water south of me in Houston. And they've got limited bandwidth. It's very expensive, but they do have huge amounts of data they want to send back. And if they could do it near real time, it would be much better than just batching it all up and shoveling it over, when they could.
We Yeah, we've experimented with compression, and it's kind of hard to get it right. So it's kind of experimental, but
Yeah,
typically the cost of compression isn't worth the sort of CPU rates that will slow things down.
yeah,
The exception is if you have something highly compressible. So say if you had a text file that was, a few hundred megabytes or something, that's
yeah,
going to compress down to, 1 megabyte or something really small. And so probably compressing that beforehand would be worth it. But what happens is if you're trying to compress it in real time, kind of as we're reading it,
yeah,
the compression won't be as good because it's the like with text, the more text you sort of feed into the compression, the smaller it will get. And we can't sort of read the whole file, compress it, and send it off in one. I mean, we could, but if you were going to do that, it's better to do it outside of the Aspera process. So what we've experimented with is doing it kind of in real time, and we limited how much data you could compress at any one time. So I think it was 64 megabytes was sort of the maximum we'd allow into these buffers and compress them down. So yeah, it kind of depends on the use case, and like a lot of our customer base is media and entertainment, and those video files don't really compress. And so there's a lot of like data out there that's sort of binary data, and it's not compressible. So you end up wasting CPU cycles to maybe save just a little bit of data space. The
yeah,
exception for sure is text files. So those compress down really quite a bit.
yeah. I'm thinking, it's interesting because the more you compress, the bigger the window you want to do the file on for compression,
Yeah,
the more delay you're introducing because you're like, oh, I'm
exactly. Yeah,
waiting for more data before I compress, and
yeah,
you kind of kill the purpose of it. Yeah, yeah.
yeah,
I do think the media and entertainment are definitely the first on this, and they get it. I
yeah,
do think there's more and more use cases because the amount of remote work that we're seeing. Don't mean work from home, but I mean
yeah,
actual. There's a camera somewhere. It's monitoring an asset. The experts are sitting somewhere else in a
yeah,
centralized location, and this is the real use case that I did about 12 years ago, 11
okay,
years ago up
yeah,
in North Dakota in the Bakken,
yep,
where monitoring oil wells remotely, and they basically built Wi-Fi towers to try and get rid of the connectivity issues, and then basically had IoT devices. But a cheaper and better way to do it would just be a camera with a 5G or 3G,
yeah,
even 2G connectivity that could at least stream back data off the devices and
yeah,
handle the connectivity issue that it will get there. It doesn't have to be fast, but it will get there. And
yeah,
those are real. The number of oil wells that are in the US, for example, alone is in the millions.
yeah,
And the cost to send people to monitor those oil
oh yeah,
wells really is ridiculous.
yeah, yeah,
And safety wise, it's not really something you want to be doing. Imagine
yeah,
North Dakota in winter. So
yeah,
having
yeah,
something that you could actually transfer that data in near real time, but transfer it reliably.
yeah,
So instead of sending a person out would be huge, and not
yeah,
do unnatural things like build your own Wi-Fi network in a frozen
yeah,
tundra.
yeah.
This,
We
those are the sort of things that would be very useful.
Yeah, it brings to mind another use case. We have a fast food provider that their network connectivity is satellite. So every store's point of sale machines, everything, they have some ancient Windows box sitting there, and so they have installed Aspera software on those Windows machines, and now they can transfer all the receipts and what have you that coming from the point of sale machines back to the central facility for
Yeah,
processing. And it's not a huge amount of data, but it's reliable, and they can bank on it that every day we're going to get our few megabytes or whatever, and it's going to transfer in a few minutes.
yeah.
um, yeah,
Yeah, I do think, personally, I think the mobile aspect is a huge piece because it now brings this sort of ability to do real-time streaming to the masses in a way.
Yeah,
So smaller
indeed.
companies that you
Yeah.
don't need specialized equipment anymore. You can actually, send your people out in the field and do things like that remotely. We're just coming up to the end of time here. There will be an office hour starting in about 5 minutes, actually. The slides are here at the bottom of the screen. Tech community, get on there for questions and for vlogs and for everything else. Aspera, as I said, not just file transfer. Think of it as reliable, guaranteed reliable transfer at the speed that it can be transferred at, depending on your connectivity, versus your old way of, I sent it, it didn't happen, oh, let's try it again tomorrow. This is a much, much, much better way to do it. And the use cases are growing all the time, you'll see, for this sort of technology. So with that, I just want to thank Ben Forsyth. Thanks very much. It was a very interesting session. Wish I had this, 15 years ago for some of my oil well issues.
Yeah.
But good talking to you, and catch
All right,
everybody.
great.
In the office.
Thank you so much, Frank. Yeah, thanks for
Bye, all.
hosting.